Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structural analysis, force, and displacement methods. Introduction to force and displacement methods of structural analysis. Indeterminate structures are being widely used for its obvious merits. It may be recalled that, in the case of indeterminate structures, either the reactions or the internal forces cannot be determined from equations of statics alone. In such structures, the number of reactions or the number of internal forces exceeds the number of static equilibrium equations. In addition to equilibrium equations, compatibility equations are used to evaluate the unknown reactions and internal forces in statically indeterminate structure. In the analysis of indeterminate structure, it is necessary to satisfy the equilibrium equations, implying that the structure is in equilibrium. Compatibility equations. Requirement if for assuring the continuity of the structure without any breaks, and force displacement equations, the way in which displacement are related to forces. We have two distinct methods of analysis for statically indeterminate structure depending upon how the above equations are satisfied. Force method of analysis. Displacement method of analysis. In the force method of analysis, primary unknown are forces. In this method, compatibility equations are written for displacement and rotations, which are calculated by force displacement equations. Solving these equations, redundant forces are calculated. Once the redundant forces are calculated, the remaining reactions are evaluated by equations of equilibrium. The force method is also called flexibility method or method of consistent deformation. It is used to calculate reactions and internal forces in statically indeterminate structures due to loads and imposed deformation. Force method is based on transforming a given structure into a statically determinate primary system and calculating the magnitude of statically redundant forces required to restore the geometric boundary condition of original structure. In this method, convert the indeterminate structure to a determinate one by removing some unknown forces support reactions and replacing them with assumed, known unit forces. Using superposition, calculate the force that would be required to achieve compatibility with the original structure. Unknowns to be solved for are usually redundant forces. Coefficients of the unknowns in equations to be solved are flexibility coefficients. The basic steps in the force method are as follows. Determine the degree of static indeterminacy, of the structure. Transform the structure into a statically determinate system by releasing a number of static constraints equal to the degree of static indeterminacy, n. This is accomplished by releasing external support conditions or by creating internal hinges. The system thus formed is called the basic determinate structure. For a given released constraint J, introduce an unknown redundant force R. J, corresponding to the type and direction of the released constraint. Apply the given loading or imposed deformation to the basic determinate structure. Use suitable method to calculate displacements at each of the released constraints in the basic determinate structure. Solve for redundant forces R. J equals 1 to n, by imposing the compatibility conditions of the original structure. These conditions transform the basic determinate structure back to the original structure by finding the combination of redundant forces that make displacement at each of the released constraints equal to 0. Types of force method / flexibility method / compatibility methods. Virtual work / unit load method. Method of consistent deformation. Three-moment theorem. Castigliano's theorem of minimum strain energy. Maxwell-Morse equation. Column analogy method. Displacement, stiffness, method. Express local, member, force displacement relationships in terms of unknown member displacements. Using equilibrium of assembled members, find unknown displacements. Unknowns are usually displacements. Coefficients of the unknowns are stiffness. Coefficients. In the displacement method of analysis, the primary unknowns are the displacements. In this method, first force displacement relations are computed and subsequently equations are written satisfying the equilibrium conditions of the structure. After determining the unknown displacements, the other forces are calculated satisfying the compatibility conditions and force displacement relations. The displacement-based method is amenable to computer programming and hence the method is being widely used in the modern-day structural analysis. Difference between force and displacement methods. Force methods. Displacement methods. Also known as method of consistent deformation. Theorem of least work. Column analogy method. Flexibility matrix method. Also known as slope-deflection method. Moment distribution method. Connie's method. Stiffness matrix method. Types of indeterminacy. Static indeterminacy. Types of indeterminacy. Kinematic indeterminacy. Governing equations. Compatibility equations. Governing equations. Equilibrium equations. Force displacement relations. Flexibility matrix. Force displacement relations stiffness matrix. The slope deflection and moment distribution methods were extensively used for many years before the computer era. In the displacement method of analysis, primary unknowns are joint displacements, which are commonly referred to as the degrees of freedom of the structure. It is necessary to consider all the independent degrees of freedom while writing the equilibrium equations. These degrees of freedom are specified at supports, joints, and at the free ends. Degrees of freedom. When a structure is loaded, specific points called nodes will undergo an unknown displacement or rotation. The number of these unknowns specifies the degrees of freedom for the structure. Nodes are commonly located at supports that allow rotation. The end of cantilever, which have both displacement and rotation, and joints in frames, which can both move and rotate. In 2 dimensions, such as the figures shown, each node can have a maximum of 2 displacements and 1 rotation, delta x, delta y, and theta. For the frame above, if delta b equals delta c, then these would only count as one unknown. Identifying the degrees of freedom in a structure is the first step in applying any displacement method of analysis. Once identified, the deformation of the structural members can be completely specified and the loadings within the member obtained. Slope-deflection equations. The slope-deflection method is so named because it relates the unknown slopes and deflections to the applied loads on the structure. It is basically the force method backwards. It has the advantage over the force method in that it requires less work to write and solve the necessary equations, and it is flexible and easily programmed. In order to develop the general form of the slope-deflection equations, we will consider a typical span above constant cross-section with a continuous load as shown. We want to relate the beam's internal end moments m, ab, and m, ba, in terms of its 3 degrees of freedom, theta a, theta b, and delta b. The slope-deflection equations can then be obtained by using the principles of superposition by considering separately the moments developed at each support due to the displacements and then the loads. Angular displacement at a, theta a. Consider node A of the member shown to rotate theta a, while the far end node, B, is held fixed. To determine the moment m, ab, needed to cause this displacement, we will use the conjugate beam method. The vertical shear at A acts downwards, positive, since the moment at A acts clockwise, positive. The deflection of the real beam is to be zero at A and B, and therefore the corresponding sum of the moments at each end A and B of the conjugate beam must also be zero. Summing the moments about each end of the conjugate beam yields M AB equals 4EIL theta A M BA equals 2EIL theta A. Angular displacement at B theta B. The angular displacement at node B is determined in the same way as theta A above M AB equals 2EIL theta B M BA equals 4EIL theta B. Relative linear displacement delta. If the far node B of the member is displaced relative to A, so that the chord of the member rotates clockwise, positive displacement, and yet both ends do not rotate, then equal but opposite moment and shear reactions are developed in the member. As before, the moment M can be related to the displacement delta using the conjugate beam method. Due to the displacement of the real beam at B, the moment at the end B on the conjugate beam must have a magnitude of delta as indicated. Summing the moments about B, we have M AB equals M BA equals -6EIL2 delta. Fixed end moments. In general, the linear and angular displacements of the nodes are caused by loads acting on the span of the member, not by moments acting at its nodes. In order to develop the slope-deflection equations, we must transform these span loadings into equivalent moments acting at the nodes and then use the load displacement relationships derived above. This is done by finding the reaction moment that each load develops at the nodes. Consider the fixed support member shown is subjected to a concentrated load at its center. The conjugate beam for this case is also shown. Since we require the slope at each end to be 0, sigma f plus equals 0. 0 equals 1/2 times PL/4EI times L minus 2 times 1/2 times M/EI times L. M equals PL8. This is called the fixed end moment, FEM. Assuming these FEMs have been computed for a specific problem, we have MAB equals FEM, AB MBA equals FEM, BA. Slope-deflection equation for an internal span or end span with far end fixed, if the end moments due to each displacement and loading all of the equations written above are added together. The resultant moments at the ends can be written as the general slope-deflection equation. M N equals 2EIL 2 theta N plus theta F 3 delta slash L plus Fem N, where instead of using the terms A or B to describe the nodes, we use N to describe the near end of the span and F to describe the far end of the span. The general equation is also often written as M N equals 2ek 2 theta N plus theta F 3 psi plus Fem N, where K is the span stiffness, K equals I/L, and psi is the span rotation of the chord, psi equals delta/L. N is measured in radians, clockwise is positive. When used for the solution of problems, this equation is applied twice for each member span, AB, that is, application is from A to band from B to A 4 span ab in the figure shown. Pin-supported end span. Occasionally an end span of a beam or frame is supported by a pin or roller at its far end. When this occurs, the moment at the roller or pin must be zero, and provided the angular displacement, theta b at this support doesn't have to be determined, we can modify the general slope-deflection equation so that it only has to be applied once to the span rather than twice. Slope-deflection equation for an end span with a pin or roller supported far end. The general equation for an end span with a pin or roller supported. Mn equals 3EIL theta n delta/L plus Fem n. Since the moment at the far end is zero, only one application of this equation is necessary for the end span. This simplifies the calculation process since only application of the equation is redundant and one of the angular displacements, theta n or theta f, does not need to be found. Worked examples. General procedure. The general procedure for solving problems with the slope-deflection equations is as follows. Label the supports and joints, nodes, and draw the deflection shape of the structure to identify the number of degrees of freedom each node can have an angular and/or linear displacement. Use the appropriate slope-deflection equation to relate the unknown moments applied to the node to the displacements of the node. Fems can be determined as shown above or may be taken from tables for Angevin load geometry. Write an equilibrium equation for each unknown degree of freedom for the structure. Each of these equations should be expressed in terms of unknown internal moments as specified by the slope-deflection equations, and substitute the slope-deflection equations into the equilibrium equations and solve for the unknown joint displacements. These results are then substituted into the slope-deflection equations to determine the internal moments at the ends of each member. Thank you for watching. Different methods of force and displacement methods calculation will be discussed in another video. For now, please subscribe, like, share and do not forget to press bell icon.